So 5-5 functions. And we need to understand what is a function. So far, we have been talking about relations. So what's a relation? Just for review, what does a relation mean? It's a, It's a set of ordered pairs. Okay, so whenever you have ordered pairs in a set, that's a relation. So you can have a relation with just 2 ordered pairs, or 3 or more, or a big amount of ordered pairs. But functions are special. They are special relations. They are not your typical relation. So not all relations are functions. And that's how we get that logic there. Are all functions relations? Yes. Are all relations functions? No. So that's a logical thing, and you have to think that through sometimes. Like, wait, are you sure, Mr. Straight? I hope we are. Yes, sir. Oh, the vertical line test? There you go. Yes, sir. Okay. And I'm going to restate because I think the wording was hard last year, and it's still hard. It's kind of like you got to be very particular on what is said so that you can be able to say, yes, that's a function, or no, that is not a function. Yes, ma'am.
Do you have
Math help tomorrow morning, 7:30. So tell your friends. Here, yes.
7:30.
You can bring breakfast if you want.
Can we eat food in here? Can we have things other than water in here?
Actually, now that I think of it, probably not. Just because they want to keep this carpet nice. I understand. Yes?
My mom said it was good for December 2nd.
Awesome. Good. I'll put you down. All right. We have a function, which is a special relation. I'll put a special relation just to make it fit into the sentence. So functions are special relations. Actually, I need that S now. Did I look at it again? In which each element of the domain, and we understand what the domain is now, I hope. What's the domain? The set of x values. So we know that is paired, and this is the key wording of this definition, is paired with exactly one, and I'll put here range element, or element of the range. All right, and that the wording means what it says, and you got to be careful with that. So it says functions are special relations in which each element of the domain, so each x value, is paired with exactly one element of the range. So what is the range again? Set of y values. So each x value has exactly one y value.
Wait, is there one that's like opposite of a function? So each of the y values is paired with exactly one of the x ones?
So that's a good question. That's not something out of this grouping here, but we are going to talk about that. What if each y value is paired with exactly one x value? Is that a function? So we'll have to answer that too. And, go ahead.
Like, is there like a different
term? No. It's just you're just talking about your domain and functions in this set. Not that I know of, Josh. So I'll say it like that. Not that I know. Okay, but there might be. Example 1. It says determine whether each relation is a function. Explain your answer. So when it tells you to explain, you can do that verbally here. So here we have a set of ordered pairs, which is also known as a close relation. It's definitely a relation because it's a set of ordered pairs. Can someone read off those set of ordered pairs so I can write them up on the board? Yes, Riley?
3, 0, 5, 2, -1, -2, and then 4, 1.
4, 1. Thank you. Okay, so here's our set of ordered pairs. Now, this is where it gets tough with that definition. All right, look at all your domain values. So kind of picture them there or look at them. Does every domain value have exactly one y or range value? Okay, so 2 has 3. 3 has 0. 5 has 2. -1 has -2. And 4 has 1. So that is true. Every x value, so all these first coordinates, have exactly one second coordinate. So we would say, yes, it is a function. This is a function, and you just explained it. Every x has one y value. Okay, B. Do you guys remember what B is called, that whole diagram? Yeah, it's just a mapping or a circle mapping. And this one has your domain and your range and the elements listed out here. What are the domain elements, Benton?
2, 3, 5, -1.
Okay, and what are the range values, Vivian? Excuse me.
0, -6, and 10.
Wait.
Oh, wait, my bad. I said the wrong thing.
Oh, that's okay. I gotcha. Do you want to get me the right thing?
Yes.
Go ahead.
Yeah. 3,
Uh-huh.
4,
Uh-huh.
-3, and then -8.
Okay, so here we go, and the range should be okay. All right, and then we have these little arrows here, and just make sure that I got it. Okay, this is a circle mapping example 1B. Okay, does does 3 only have one y value? Okay, does 4 only have one y value? 4 only has one y value.
Yeah, correct.
Does -3 only have one y value? Does -8 only have one y value? Okay, now it's tricky, right? But don't -3 and -8 have the same y value?
Yes.
But that doesn't change the fact that it's a function. So if I look at this, if I had ordered pairs with those two, I'd get -3, 10, and -8, 10. The definition said that every element in the domain has exactly one element in the range. So that's true so far. And even here it's true. When would this not be a function? So can anyone give me an example where this would not be a function? Or on the circle mapping. Ellie?
Like if -3 was like it was the ordered pair was -3, -6, and -3, 10.
Yeah, if -3 had an arrow going to -6 and 10, no longer a function. Because now this element has two y elements or range elements. So that one is good. That one is a function, yes. This one is a yes. And then C. We'll keep going through it because I know it's kind of tricky. C, you have a table. I'm not going to create that table. Does every x value have only one y value? For C.
No.
Wait, what? Which x value has more than one? 5. 5 gives off 2 and 3. Not a function. Not a function, or no. So that last one was yes. This C is no. Okay? So you see how you can look at the circle mapping, the ordered pairs, or the table to determine whether you have a function or not. So far, so good? Okay? All right, let's do this real quick. Look on page 291, and I want you guys to do number 6 and 7. Just say yes or no. 6 and 7. Don't say it out loud, but write it on your paper. 6 and 7. Tell me if it's a function or not. They're both relations. We already know that, but are they functions? That's what we're trying to figure out. Okay, number 6. Is 6 a function? Everybody?
Yes.
Oh, good. Yeah, because every element in the domain gives off one and exactly one element in the range. Even though 6 and 2 give off 3, it's still one for each of the domain values. All right, what about 7?
No.
Oh yeah, that 5 again gives it. Wow, it's the same as the other one, or very close. Okay, but 5 gives off 3 and 4. What about 8? What? That's so strange. Okay, how'd you guys know that?
Vertical line test.
Ah, the vertical line test. Okay, vertical line test. Which you guys remember from years past, vertical line test is a test you can use on the graphs of a relation. So on example 3, we're going to use that vertical line test. And we'll do it on A, B, and C. Okay, so you're like, what's a vertical line? Can someone describe a vertical line or show me a vertical line? Yeah, you just hold up your writing utensil up and down. That's a vertical line. So vertical. All right, you can use that pencil or that vertical line object or your finger or your imagination to look at A. Now look at 3A, example 3A. Does that vertical line pass through 2 or more points at the same time on that graph? If it passes through 2 or more, it has failed the vertical line test. And A, is that a function or not? No. Not a function. No, not a function. And I'll do a sketch here. Is anyone missing today from this class? Oh, Harper. Okay, good. So here's my graph. Wow. Listen. It's back there. Vertical line test. You see where the shadow hits 2 or more points? No longer a function. All right, B. B is what kind of line is that, by the way? Horizontal line. And you can even see the shadow. Does my shadow of the vertical line ever hit 2 or more points? No. So it passed the test. It is a function. Yes, function. And then C. Uh-huh. You can put yes or no. I'll let you do yes or no. Yes. Yes, that's correct. Okay, so here's my third. So does my shadow, which I will make bigger now. Whoa. Does it ever hit 2 or more points? Yep. So it's not a function. Not a function. No. You guys get that vertical line test? Pretty straightforward. Okay. Look at number 13 on page 291. Number 13. Don't say it out loud yet. Is that a function or not? Number 13 on 291, I think I said. Yeah, 291. So just come up with your answer. Does it pass the vertical line test? Okay. And Margot, is number 13 a function or not? No. So you just put no. No, N-O. Or not a function. Or negative. Okay, I think you guys get those. Last part. This is the toughest part. Oh, no. Yeah, you can't get that. It can't stay that easy. Although you have done this before, it does get a little bit complicated. Okay, functional notation. I like functional notation, although when I was younger, about your age, I did not like it. Like, why can't they just say y? Why do they have to say f of x? Well, there's something that's special about f of x. So let me give you an equation. Y equals 3x minus 7. Okay? This is how you normally see your equations. You've seen this before. Nope. You should be comfortable with it. Okay. When you're dealing with a function, you're dealing with a special type of relation, right? So it's kind of special. It's unique. And therefore, I can write this equation in functional notation. So this is normal. Functional notation would be something like f of x is equal to 3x minus 7. So go ahead and write that down, and I'll have us say it so we know how to at least say it. So write that down. That's functional notation. It's the way you're going to see a lot of equations from here on out. Okay, you're like, okay, that's f of x equals 3x minus 7. Can everyone say it with me? F of x equals 3x minus 7. I just have a quick question. What happened to y? It's got wiped off the earth.
It's right there.
This is y. This whole thing is y. And you're like, why can't they just put y? There are many reasons why they can't put y, but the biggest reason is this. If you have a function, it's a special relation, and they want to show that special relation this way. They want to tell you that x and y are linked together in a special way. And that special way is this. That's a special way. You're like, well, that's so special about it. If you grab it, you'll see it. But anyway, they're saying that instead of just saying y, say f of x because x is part of y. Like, what is x again? Domain. And domain deals with which one of those variables? Independent or dependent? Independent, right? X is independent. So doesn't y depend on x? So y is not only just y anymore, it's something about x. It's related to x in a special way, and that's why we say x is independent and y is dependent on x. So that's showing that right there. Right there, showing it. The letter y. How about that? Maybe I should, yeah. So x, the y here, the letter y, depends on what x is. And that's what it's showing you in functional notation. All right, but it's actually not hard to work out. Example 4. Let's look at example 4, how we actually use it. It says, if f of x is equal to 2x minus 9, then find each value. Okay, so that's our equation. And for A, they want me to find f of 6. F of 6, we would say. Okay? So all they want you to do is replace each x with the number 6. That's all you do. Okay, so look at the original equation. Ready? F of 6 is equal to 2x minus 9. Or, wow. 2 times 6 minus 9. That's all they want to do. Just replace x with 6. Well, and then you have to find out what is this. Yeah, what's this value? So what's 2 times 6? 12 minus 9? Okay, so you would technically say f of 6 is 3. That would be your answer right there. F of 6 is 3. Yes. Can't believe I'm doing that, but yeah, go. Oh, no, don't think of this as like a value that you need to solve for. No. This is one thing together. It's like one special thing together. In fact, don't we normally say if we have a variable and a number, don't we normally put the number first, then the variable? Yeah. So this is like incorrect format for that. So don't think of it like you're solving this. You're solving for f. No, this is one thing. F of 6 is equal to 3. Okay, let's look at B. You're trying to find B, what f of negative 2 is. So what you have to do on this problem is substitute negative 2 for every time they have x. So f of negative 2 is equal to 2 times negative 2 minus 9. 2 times negative 2 minus 9. So what is 2 times negative 2 minus 9? Well, what's 2 times negative 2? Negative 4 minus 9? Oh, yeah, so I'll just leave it like that. You can put negative 13. That's it. It's an evaluation problem. Uh-oh, C. Oh, boy. Now, this one's just not even cool because they just did something different. F of k plus 1. What? 2 variables of 1? What do you think you have to do in this problem? Substitute every time you have x with k plus 1. So 2 times k plus 1 minus 9. You just replace k plus 1 for x. And you're like, hey, we can't do that. Can you? Can you do this?
Yes.
What property?
Distributive.
So you're going to do 2 times k is 2k. And 2 times 1 is positive 2 minus 9. Can you make that any simpler?
Yes, you can.
Yeah, so combine these two like terms, and you get 2k minus 7. That's the simplified version. Okay? So if you put k plus 1 in for x, in this function you're going to get 2k minus 7 for y. So there's an ordered pair here. It's very complicated. Ready? How many of you see that? So it's an ordered pair. So what's this first value? X. But what's x? K plus 1. And what did you get for that y? This is a point on the graph. You're like, I don't know what it is. I don't know what it is either. What do we have to find out later in this problem? Just find out what k is. You'll get a number. I just don't know what k is right now. But if you did, you could easily put that on a graph.
That's cool.
It is cool. I think it's really cool. All right, last example, and then I'll let you go. Okay, example number 5. It just took it up a notch. Oh, my. Can someone read that problem for me properly? Read it for me in the proper way. I know it's tough, but it's not F anymore. It's H. Riley? H of Z is equal to Z squared minus 4Z plus 9. All right, so that's my problem. And then A, they say find H of negative 3. H of negative 3. What do I do in this one? There's no X. There's no more X's in this one. Instead of the Z, what do you replace it with?
Negative 3.
Okay, so here you go. Instead of Z, you put negative 3. So it's now negative 3 squared minus 4 times negative 3 plus 9. So solve that, or sorry, I should say simplify that. So what's negative 3 squared?
9.
Positive 9. What's negative 4 times negative 3?
12.
Positive 12 plus 9. So what's your final value?
30.
Positive 30, good. So H of negative 3 in this equation is 30. Okay? Guys, good so far on that? And then we turn the page. Uh-oh. They did another one like they did on the last example. Now they have H of 5C. H of 5C. So what do you think you have to replace Z with?
Oh, no.
5Z. All right, ready? So 5C squared, what was it? Minus 4 times 5C plus 9. Oh, man, that's a headache waiting to happen. All right, you're looking at it. I don't know. What's 5C squared?
It's 25.
It's 25C squared. Because what's 5C times 5C? Well, we know that's 25. And then C times C is C squared. And then what's negative 4 times 5C? Negative 20C plus 9. Are there any like terms? Any way to simplify that more? No, don't these look like terms? But there's one thing that's not so like about them. Yeah, one squared, one has a 1. This is your final answer. That's all you can do. And then the ultimate hardest, most difficult problem. C. Uh-oh. Look at that. I would read that. Ready? 5 times H of C. Is that okay? So I'll write that down. 5 times H of C. All right, so you're saying, I don't know what to do. First thing is I'm going to deal with this right here. What should I replace Z with? C. Right here. Just C. Just C right there. Yeah, so we get C squared minus 4 times C plus 9. So I just replace Z with C. Okay. And then we have to deal with that 5. We're going to multiply the whole function by 5. So how are we going to do that? Ready? Multiply it all by 5. So that's a big distribution problem. So what's 5 times C squared? 5C squared. What's 5 times negative 4C? Negative 20C. And what's 5 times 9? 45. That's your answer. So again, deal with the substitution. This could be a number, it could be a letter. Substitute it. And then this is outside that function, so you multiply the whole the whole expression by 5, and you get that.
I understand how you did everything, but I don't understand like the brackets around H.
Okay, so you understood this first part? Okay. And then this is saying that the whole function is being multiplied by 5. So whatever that function equation is gets multiplied by 5.
So H and C represent the function.
Yes, H of C represents a function. And that's functional notation. There's a relationship that's special. Now, make that special thing times 5. Up it by 5. Okay, your homework tonight and you know what I'll do? I think it's due on Monday. So we have a quiz tomorrow, as you guys know. And we're going to review tomorrow morning. You can do it before school, and you can do it, and a lot of you will do it first hour. But then this homework assignment is due on Monday. I would get it done as much as you can and not even worry about it, but that's up to you. Okay, so your homework is 19. You know what? I think I'm going to go 19 to 49. Odd.
You just make it longer.
No, stop. He's doing odd.
Yeah, it doesn't matter.
Doesn't matter. Okay.
That's like 15.
No, Ellie, I did make it longer, but I think you guys can handle it. That's why. Like at first, I'm like, I don't know if they'll get this, but sometimes you will. If you wait till Sunday night to do this, though, this might kind of slip out of your mind. So I would say try to get it done. You have the rest of the class time. Sorry?
Do we have time after the quiz?
Yeah, you might have some time. Yep. So you can get that done. All right, bye.